diffusion models have achieved remarkable success in image generation, but come with significant computational costs, posing challenges for deployment in resource-constrained environments. Recent post-training quantization methods have attempted to mitigate this issue by focusing on the iterative nature of diffusion models. However, these approaches often overlook outliers, leading to degraded performance at low bit widths. A natural approach to mitigating outliers is equivalence scaling, originally introduced for LLM's quantization, which scales the activations channel-wise and compensates for this scaling by inversely scaling the weights. It reduces quantization difficulty by transferring the challenges of outlier channels in activations to non-outlier channels. Existing work in LLMs determines scaling factor based on the ratio of maximum activation and weight magnitudes. Although this approach has shown promise in language models, its naive application often fails for several reasons. First, inaccurate scaling factors can drastically degrade output quality. As shown in right table, smooth quant results in poor performance for diffusion models. As shown in the figures, smooth quant yields large scaling factor, which significantly increases quantization range of weight and in turn amplifies weight quantization errors. Second, equivalent scaling redistributes outliers between activations and weights, but does not eliminate outliers. To address these issues, we propose DMQ, a new post-training quantization framework tailored for diffusion models. DMQ unifies two key techniques: learned equivalent scaling and channel-wise power of two scaling. First, LES learns accurate scaling factors that balance quantization difficulty between activation and weight by minimizing overall quantization error. Second, to handle extreme outliers that remain unresolved by equivalent scaling, we introduce PTS. Unlike LES, PTS directly removes extreme activation outliers by scaling them with power of two factors. Our goal is to reduce quantization errors by optimizing channel-wise scaling factors. In a diffusion model, the activation distribution varies dynamically across time steps. Therefore, it is crucial to carefully analyze the behavior of quantization error over time steps. To investigate this, we initially quantize the network and measure average quantization error. As illustrated in figure, the quantization error increases as denoising progresses. This observation raises a central question. Does a higher quantization error at a specific time step correlate with the final image quality? To answer this, we probe the diffusion model by injecting small random noise. As shown in the figure, the final output quality does not directly correlate with the quantization error across time steps. Specifically, while the later time steps exhibit larger quantization errors and significantly degraded FID scores, the earlier time steps also substantially affect the final image quality despite having smaller quantization errors. This is due to the fact that errors at early time steps accumulate throughout the denoising process, ultimately impacting the final image quality. Applying a uniform loss across time steps is suboptimal, as later steps typically exhibit larger errors, biasing optimization. Thus, naively prioritizing early steps can overlook critical later steps in certain layers. To address this, we propose an adaptive time step weighting that dynamically adjusts weights based on the observed quantization error. This design is inspired by focal loss, which emphasizes harder to classify samples by assigning larger weights. Similarly, our approach prioritizes critical time steps with lower accumulated errors. Specifically, a higher alpha shifts optimization toward early denoising steps, where small quantization errors can still significantly impact final output quality due to error accumulation. Upon examining activation distributions in the diffusion model, we found that some layers, especially skip connections lacking normalization, exhibit significant interchannel variance due to extreme outliers as shown in the figure. This high interchannel variance poses substantial challenges for quantization. Although LES reduces quantization errors by redistributing difficulty between weights and activations, it alone cannot fully mitigate these extreme cases, which pose substantial challenges for quantization. To address these challenges, we introduce a channel-wise power of 2 scaling for activations. This approach scales activations on a per-channel basis using power of 2 scaling factors, effectively adjusting the dynamic range of each channel individually. As shown in the below figure, when power of 2 scaling is applied, the activation outliers are further diminished, demonstrating power of 2 scaling in reduces extreme activation values. Multiplying by a PTS factor is equivalent to shifting the bits of the product, which is highly efficient on hardware. Selecting an appropriate PTS factor is crucial for minimizing error. If the factor is too small, large salient activations are not sufficiently scaled down, pushing them outside the quantization range and causing severe clamping errors. In contrast, if the factor is too large, the activations are overly compressed, increasing the rounding errors. A straightforward approach is to select the values that minimize quantization error over the calibration set. However, as shown in the table, we found that this degrades the model's performance on unseen data, making it unsuitable for PTQ, where only a small calibration set is available. To overcome this, we propose a robust voting algorithm for selecting the PTS factors, which remains effective even with a small calibration set. As illustrated in the left figure, the voting algorithm for PTS factors comprises the following 2 major components: candidate selection by per-channel quantization, and in robust voting mechanism by thresholding. This conservative approach prevents significant activation distortion by rejecting scaling factors with low agreement, thereby avoiding excessive clamping errors that arise when inappropriate PTS factors push activations beyond their typical quantization range. Next, we present several experiments that we conducted on unconditional generation. As shown in the table, our method consistently demonstrates superior performance across all settings and outperforms most existing methods. Notably, baseline methods, which do not consider outliers, suffer significant performance degradation at W4A6, whereas our approach maintains high FID and SFID. Qualitative results in class conditional generation are shown in the below figure. Except our approach, baselines shows degraded image quality in W4A6 setting. In contrast, our approach shows almost similar results with full precision. As the conclusion, we present a new approach that addresses the outlier problem in diffusion model quantization. By integrating learned equivalent scaling with an adaptive time-step weighting, we redistribute quantization difficulty between weights and activations and prioritize critical time steps. Additionally, we propose a power of 2 scaling, accompanied by a robust voting algorithm, to handle layers with extreme outliers, such as skip connections.